right, hello everyone. Thank you so much for joining. I'm Justine Kochi. I'm a program manager on the Azure Cosmos DB team. And today I'm really excited to talk to you about architecting highly resilient applications in Azure. Now, if you've been to other sessions at Build, you've probably heard a lot about AI features. There's not going to be any AI in this talk. We are focusing on planning, architecting, and monitoring resilient applications. So we're going to use an e-commerce website as an example for the resilient app that we're building. This is a website where users can browse for products, they can add products to their cart, and they can check out. If we look at the architecture of this application, we have our front end, which is deployed on Azure Web Apps. We have a set of microservices that are deployed on AKS, Azure Kubernetes. And each of these microservices talk to their own container in Azure Cosmos DB. In Azure Cosmos DB, we're using our NoSQL API. And Azure Cosmos DB is a distributed database, which means it can scale out as we add more data and we need a larger database to store our data and satisfy our user requests. As we look at the user interaction flow for our website, it starts with a user logging in. Then they can browse products on our site, they can add products to the cart, they can check out, they'll create an order, they'll pay for the order, and then our website will make sure to go update the inventory so that we have accurate stock counts. Now, as an application developer, I actually care about different things at different points in this user journey. If I look at the beginning of the user journey, where customers are browsing my site and they're adding products, I want to make sure that my site is highly performant and highly available. Before they've added anything to their cart and checked out, I want to make sure that my site loads quickly, that we're able to search for products efficiently. At this stage, users are very vulnerable to churning away from my site if it loads too slowly. So performance and availability are really top of mind at this part of the journey. However, towards the second half of the user journey, where users are actually making their orders and paying for these products, my priorities shift a little bit. In this section of the user journey, I really care more about consistency and availability. I want to make sure that when an order is made, I keep that order. We don't want to miss any of our dropped orders. We don't want to have any payments go through twice. So when I think about the requirements at different parts of the user flow, it will inform how I build my application. Let's take a look at some key concepts so that we can plan for resiliency up front so that our application remains highly responsive and is able to satisfy our user requests. We're going to cover some design principles for building resilient applications. First, in a distributed system, things will go wrong. So we need to plan for failures up front. We'll look at several self-healing remediation tactics that we can use to ensure that when something inevitably goes wrong, our system is able to automatically handle the failure and reduce dependency on human intervention. We'll look at ways to minimize the blast radius so that when something goes wrong, it doesn't cascade out into every part of our system. And lastly, we'll take another look at our business requirements and see how requirements at various stages in the user journey might inform how we implement our application. A lot of the guidance that we'll go through today is available on the Well-Architected framework. There is a ton of guidance on this framework, and I highly recommend that you check it out. We're going to be focusing on some of the resiliency aspects today. So let's take a look at our architecture one more time. In a distributed system, we know things can go wrong, and it's important to think about various failure modes and categories of things that can go wrong so that you can accurately plan and prepare before it happens. Looking at my architecture, there's a couple of areas that I know I should plan for. First, network failures. We could have failed requests, we could have packets dropped, DNS issues. We want to look at planning for that up front so that they don't impact the user experience. We also may have something go wrong with our APIs. We may have pods go down in AKS. So how can we plan for that up front? And lastly, we'll look at failures that can happen in the database and how we can use strategies to mitigate those. So first, looking at the network, there's many things that can go wrong with the network, and there's several remediation strategies that we can implement to recover from them. If we have failed requests, we can implement a retry policy. It's always a good idea to have retries in your application to retry a request if something fails. However, adding this with an exponential backoff strategy means that we have an increasing delay in between retries and increases the likelihood that the next request will actually succeed. However, I don't want my site to be in an infinite retry loop if something is not going to succeed, right? That would lead to a very bad user experience and could end up having an overall very high latency. So we can couple our retry policy with timeouts and fail fast logic. You can have, for instance, maybe a 5-second timeout and couple it with a circuit breaker for repeated failures to help give the system time to recover. We're going to dive much deeper into the circuit breaker pattern and show an example of what this looks like in our application a little bit later on. Lastly, with the network, you could have DNS issues. You can implement a traffic load balancer like Azure Front Door, which will automatically reroute traffic. In my application, I have this deployed globally. If one region becomes unavailable, Azure Front Door can automatically reroute traffic to the healthy region. It doesn't update the DNS records directly, but it actually uses a layer 7 technology to quickly react to changes and reroute traffic as appropriate. All right, so those are network failures, but I know things can go wrong in my app too. So what are some strategies that we can implement here? Since my application is deployed on Kubernetes, I can use liveness pods to monitor the health of my pods as they go along. If the liveness pod detects that a pod needs to be restarted, it will restart automatically, so I don't need to manually intervene. Now, liveness probes in Kubernetes can be paired with other types of probes. For instance, a readiness probe will ensure that traffic isn't routed to pods that aren't ready to handle traffic yet. So combining your health probes can really make your application much more resilient. However, as pods are going down, sometimes they need to complete tasks. They need to clean up resources. They need to finish what they were doing before they terminated. With AKS, you can set graceful termination policies that will ensure there's enough time for a pod to safely shut down before going offline. And of course, sometimes you have more traffic, right? That's our goal as application developers. We want to be overwhelmed with traffic. But you want to make sure that your cluster is resilient and can actually handle this increased load. You can use auto-scaling and container orchestration to help tell Kubernetes how to handle scheduling more pods if you have increased traffic. There's horizontal and vertical pod autoscalers as part of the cluster autoscaler in AKS. For a horizontal pod autoscaler, this will automatically tell the scheduler to schedule more pods if you see increased traffic. Whereas the vertical pod scaler looks at resource consumption within a pod, looks at CPU usage and memory, and determines does each pod have enough resources to be successful. Lastly, we may have things go wrong in our database. Now, just like any network request, a database request can fail. So we want to implement retries for our databases as well. However, when thinking about databases, it's important to have idempotent retries. You don't want to accidentally execute a payment and have it go through twice. Double charging our customers is a really bad customer experience. When we implement idempotent retries, we can ensure that our retry policy doesn't actually ruin the customer experience when what we're trying to do is make it better. You can combine retries with other strategies like request hedging. Sometimes a retry may take a long time, as we discussed, right? You don't want to continuously retry on a region that maybe is not going to succeed. In the Azure Cosmos DB SDK, we have options for cross-region request hedging. What this does, you set a threshold. If a request takes up to a threshold, it will automatically send a hedged request to another region, and each of these hedged requests have their own independent retries. As the step threshold increases, it will continue sending hedged requests to any other regions that you have configured in your account. With cross-region request hedging, that means whichever request actually gets a completion message first, that is the one that will go through. And your overall latency can be greatly reduced. Lastly, with databases, often many connections are being opened. In Azure Cosmos DB, as a distributed database, your data lives on multiple physical partitions. Well, each physical partition is actually a set of 4 replicas. You can imagine for the SDK, this is a lot of connections to open. Using strategies like a singleton client will help the SDK better know how to pool and manage those connections instead of instantiating a new client each time and having to reopen all those connections again. So we talked about some strategies to self-heal. However, when something goes wrong, you want to make sure that it doesn't take out your entire application. So to minimize the blast radius, there are some things that you can do as an application developer. You can isolate components of your workload. Now, we talked about the microservices architecture, where our products API is separate from our cart API, is separate from our orders API. All of these are isolated, and that means that if something happens to one of them, it doesn't take down the entire system. Now, within each isolated component, you still want to ensure that you have redundancy to serve requests if a certain instance goes down. As you're adding new features to your application, you can deploy using feature flags. Feature flags are awesome because it means that if something goes wrong with the new feature that you deployed, you can easily turn it off without having this error new flow impact existing successful user flows. And lastly, it's important to have robust monitoring and alerting. It's very difficult to solve issues that you don't know exist. With robust monitoring, you can know if something goes wrong, when it goes wrong, and why it goes wrong. So it gives you a better chance of being able to fix it. As an app developer, though, you also can rely on many features that the platform gives for you. The first is availability zones. Availability zones offer fault isolation within a single region. There's 3 availability zones in regions in Azure, and each zone has its own power, networking, and cooling, which means if something happens to one zone, the other zones are still available to continue serving traffic. You can also deploy your application into multiple regions. So while zones are within a region, deploying in multiple regions gives you even higher availability. This is following the active-active pattern, which we'll dig deeper into later on. There are so many managed services in Azure that offer built-in resilience and failover features. You can take advantage of these as an application developer and let the platform do the heavy lifting for you. All right, so let's take a deeper look at our application. We have set topology spread constraints to tell AKS to make sure that we have pods on multiple nodes in multiple zones of our region. As you can see, we have our 3 APIs here, our products, cart, and orders, and there's an instance for each of these in every zone in multiple regions in Azure. If a single node goes down, then pods are still available in the other zones and other regions to continue serving traffic. If you have a voluntary pod disruption, like an upgrade or a deployment, AKS has something called pod disruption budgets that will make sure the scheduler schedules new pods before taking those pods down for these voluntary disruptions. This is extremely important because it means that no scheduled event will reduce the experience for your application. But what if an entire zone goes down? Luckily, since we have specified to deploy our application across zones, we still are able to serve traffic even in zone down scenarios. Now, some of the fears about using availability zones are latency across zones. Cross-zone traffic in Azure typically succeeds with less than 2 milliseconds. So you can get this increased availability without having to sacrifice latency in your application. Another concern we hear about availability zones is, oh, that sounds really expensive. With AKS, you pay for the compute that you have provisioned, regardless of what zone it's in. So using your deployments across zones means you get extra availability with the same cost. For Azure Cosmos DB, you get availability zone support for free when you use auto-scale throughput. There are many ways to implement availability zones while still maintaining a cost-effective structure. All right, but what if a region goes down? Luckily, since we have our application deployed across multiple regions, we're still able to continue serving traffic even in region down scenarios. Okay, so we've done a lot of planning. I think we're in a good spot, but let's check back in on our business requirements and see what else we need to think about given the priorities that we have at each stage in our user journey. We're going to look at 3 metrics. The first is our service level objective. This is the target level of service availability for your account. You might frequently hear this described as 4 nines or 5 nines. To put that in perspective, 5 nines of availability means there's only 26 seconds of downtime in an entire month. Now, looking at the next 2, RPO and RTO, RPO stands for Recovery Point Objective. This is the amount of time where data loss can occur. If I think about my user journey, that second half of the journey where I'm processing orders, I want to make sure my RPO is 0. I don't want to lose a single order for my customers. However, for RTO, Recovery Time Objective, this equates to how long you are down. For RTO, I really care about RTO 0 in the beginning of my user journey, where customers are searching for products on my website. Thinking about the business requirements at various components will help you plan for the best reliability strategy for your use case at the appropriate time. All right, I think I'm ready to start developing this application. Let's take a look at 5 architecture patterns that can help us maintain resiliency as we develop. For regional fault tolerance, we're going to use the active-active pattern. To help us protect against failing remote services, we'll implement a circuit breaker. Because we have microservices, we can use the Saga pattern to help us maintain data consistency across our microservices and compensate any failed transactions. We'll use the bulkhead pattern to help us isolate components in our application, and we'll use the cell architecture for system-level isolation. Beginning with active-active, this ensures that there's 0 downtime. Because our applications are replicated across regions, if one region fails, the rest can still continue serving traffic. Let's see how this is implemented in our application. So we have our AKS cluster, and our AKS cluster uses external storage in Cosmos DB. This means the cluster itself is stateless. As a stateless service, we can implement the active-active pattern by simply creating a cluster, 2 independent clusters in each region. Now, AKS has AKS Fleet Manager, which makes it easy to maintain consistency of your deployments across regions. With Fleet Manager, you choose what you want to deploy on your hub region, and Fleet Manager will automatically replicate that to all the other clusters in your application. This makes it very easy to implement the active-active pattern and make sure that your cluster is the same across all regions that you've configured. However, for Cosmos DB, this is a stateful service. Imagine if I implemented it the same way, where I had 2 independent Cosmos DB accounts, one in East US and one in West US. Imagine a user comes in and they submit an order in East US, but then East US goes down. So our load balancer routes traffic to West US. The user goes to check their orders, and it's not there. So for stateful services, it's important to have replication. With Cosmos DB, when you configure multiple regions in a single account, it uses automatic asynchronous replication to replicate data from one region to the other. Well, this sounds great. I think we should use it. But now that we have replication, we also need to consider consistency. For Cosmos DB, we have 5 consistency modes, and they all have trade-offs between consistency, availability, latency, and throughput. When I'm deciding which consistency mode to use, I can think back to my business requirements. So in the beginning of my product lifecycle, my customer journey, I really care about performance, right? I want my site to be highly available and responsive. In this stage, I can use eventual consistency, which gives me the highest availability, the lowest latency, and the highest throughput. However, for the middle part, where customers are checking out and adding items to their cart, I want to make sure that users can actually read their own rights. This is what session consistency gives us. With session consistency, we can ensure that users adding things to their cart and refreshing the page will always get the data that they had written seen back to them. Now, in the last part of my customer journey, this is where I want to use strong consistency for submitting my orders themselves. With strong consistency, Cosmos DB doesn't commit the write until it's actually committed to all 4 replicas in every region of your account. While this gives us really high consistency, it does have a trade-off for latency. But when I'm submitting an order, a user is a lot more likely to tolerate a small amount of latency than when they're browsing my site. So thinking about my business requirements can really help me choose the right consistency model to choose for my application. Now, for the active-active setup, there's one more decision point that I need to make, which is how do I configure the writers in my application? For Cosmos DB, you can use a multi-writer strategy. With multi-region writes in Cosmos DB, I can configure multiple regions in my account, and each of them can accept both read and write traffic. The changes to one region are automatically replicated to other regions. However, now I need to think about conflict resolution. What if the same item is updated in both regions? So there's conflict resolution policies that you can configure to handle this. Now, for my use case, I think for my orders, I don't want to deal with conflict resolution. I think I want to use strong consistency, which means I should use a single writer. I can use strong consistency, single writer, and a new feature called per partition automatic failover. With per partition automatic failover, in Cosmos DB, I still have my regions in my account. One region is the write region, which is accepting writes. However, if a single partition or a subset of partitions in that account is experiencing issues, the Cosmos DB SDKs can automatically route the writes for that region to another healthy region. This maintains high availability without sacrificing on my single writer and consistency semantics. With the multi-writer strategy, I have RTO of 0 because all of my regions are able to accept traffic and we can quickly cut over between each other. The RPO in our multi-writer is roughly equal to the replication lag between regions. With the single writer strategy, because I'm using strong consistency, my RPO is 0. The RTO is roughly about 2 minutes. So the per partition automatic failover feature allows us to get 0 downtime, 0 data loss, all with 0 touch. You don't need to manually configure which region the partition is routed to. The SDK handles all of this for you with no operational overhead. We can look at a quick demo of the per partition automatic failover, and this is a recorded demo sped up just a little bit so that we can see how the failover works and how the application is actually responding. As I play the demo, I have 2 accounts created. I have my per partition automatic failover account and a non-per partition automatic failover account. As we start these console apps, both accounts are sending writes to my Cosmos DB account. The primary write region is North Central US. Then on the third screen, I'm going to start a script which will actually take down one of the partitions. We're simulating a partition failure. As you can see, both of our console apps now start returning 503, service unavailable, the partition is down. But the per partition automatic failover account is able to quickly recover and start sending traffic to West US. Notice all of my writes are now succeeding, where the non-PPAF account is still getting those 503 errors and it's still failing. With per partition automatic failover, the routing to healthy partitions is what gives us this high availability in an active-active setup. As my partition in North Central US comes back online, you can see the non-PPAF accounts start succeeding again. And shortly, our PPAF account is able to automatically fail back to North Central US. This means that you don't need to manage your failover or failback, and it's all automatically handled for you at the partition level. So you may be thinking to yourself, okay, active-active sounds great, but it also sounds expensive. With Cosmos DB, you can use dynamic autoscale. With dynamic autoscale, each partition in each region can scale independently depending on the throughput that was actually consumed on that partition. This is cost-effective for non-uniform workloads because all of your partitions can scale based on their actual usage patterns. There's also scaling features in AKS that can help you reduce costs in your active-active setup. We've already talked about the cluster autoscaler with vertical and horizontal pod scalers. However, there's also profiles, workload profiles that you can customize in your cluster autoscaler to optimize for cost efficiency. You can set things like the amount of time a pod is unneeded before it will be scaled down or utilization thresholds. This helps you keep your application cost effective. There's also a preview feature in AKS called node auto provisioning. While the cluster autoscaler manages scaling pods, Node auto provisioning helps you provision the right infrastructure for your workload. You no longer need to pick which VM to actually deploy your application on. It uses efficient bin packing to make sure that the underlying infrastructure is the best suited for your specific workload. And it can lead to cost savings by optimizing the hardware that you're actually deploying on. All right, so we have our active-active set up, and we're able to handle failures, regional failures. But what if a service starts failing? We can implement the circuit breaker pattern to avoid failures overwhelming our downstream services. You can think of the circuit breaker pattern like a circuit breaker in your house. When there's too much electricity, the circuit breaker will flip open and stop the flow of electricity so that you don't start a fire. Similarly, in software, the circuit breaker pattern can help you stop calls to a failing service and avoid overwhelming it and making the problem even worse. The circuit breaker pattern is implemented as a state machine with 3 states. In the closed state, requests can continue flowing through, just like a closed circuit. In the open state, requests are blocked. There's not going to be any requests made to the service that's been failing. And the third state is half open. This is like a test state where we send a test call to see, am I ready to close the circuit, or do I need to keep it open and continue blocking calls for a little bit longer? Let's see how we can use the circuit breaker pattern in our application. Now, I have an Orders API here, and the Orders API is responsible for calling out to a third-party payment service to submit our payments. Unfortunately, the payment service that we're using is a little bit flaky, and we frequently get failed requests. With the circuit breaker pattern, you can keep a counter of these failed requests. As the counter goes up, we'll eventually hit a threshold. Once the threshold that we've defined is hit, it starts a timer. During this timer, this is when we're in the open state. Any requests that come through to our Orders API will not be forwarded to the payment service. After the specified amount of time, we'll enter the half open state, where the next request that we make will be tested to see, are we ready to start resuming traffic again? If this call is successful, then our circuit will close and we're able to continue traffic. Let's take a look at a demo of how this is implemented in our application. All right. So I have a .NET Aspire application here, which is going to help me make calls with my order service and connect to a simple web front end that I've configured. .NET Aspire is a cloud-ready stack for building observable and scalable cloud services. I'm using a simple web API here for my order service, and I take in an order. The first thing I want to do is call Cosmos DB and actually store this order in Cosmos. If I take a look at my order service, it's pretty simple. It does one thing. It creates an order and stores it in the database. Now, you'll notice my constructor here, I have a Cosmos client which is being injected with dependency injection. I'm using the Cosmos DB.NET Aspire component to automatically configure my Cosmos client. Now, using this Aspire component, Aspire is an opinionated stack. It has a bunch of the defaults already in place for you. So when I use my Cosmos DB component, Aspire already knows that it should be a singleton. I have some configuration configured. I can use my credential. I'm using default Azure credential to avoid the reliance on passwords. This is using managed identities instead. Once my client is configured and I've made my call to Cosmos DB to store the order, I need to call my payment service. Now here I've just implemented another web API in the same project called my flaky third-party payment, but you can imagine calling out to a real external service. My flaky payment service is hard-coded to fail 66% of the time. And when we make this request, the first thing we'll do is we'll check, was it successful? If it's successful, we know our circuit is in a closed state. Even if it failed, it may still be in the closed state. So we can print out a message and say, hey, something went wrong, but we didn't trip the circuit yet. And we're also going to look for the broken circuit exception. If we get the broken circuit exception, we know that our circuit breaker is open and it's not able to process requests. We're not even sending requests to our payment service. Now, if you're familiar with Aspire, you know that they have a service defaults project that gets created with any Aspire project. This has a set of default extensions that help you configure various things for your application. You may have seen the add service defaults function. This is configuring a bunch of defaults and best practices, adding things like OpenTelemetry and health checks and service discovery to your application. I want to call your attention to the Configure HTTP Client Defaults function. What this does is it adds a standard resilience handler, which is actually applying 5 resilience strategies in a cascading effect. When you use the standard resilience handler, it applies a rate limiter, total timeout, retry, circuit breaker, and attempt timeout. Now, this is a really great default resilience strategy. You can further customize the resilience strategy by setting options. Here, I'm modifying the sampling duration, I'm raising the failure ratio to make sure we have some interesting failures to look at today. I'm lowering the minimum throughput. Minimum throughput is important because if you only have one request in a given time period, it doesn't necessarily mean you need to trip the circuit. So this ensures that you have a sufficient volume before the circuit breaker policy takes effect. And we're also going to print some messages to the console when the state changes. However, with this standard resilience handler and all of these resilience strategies, it's difficult to make a demo that highlights circuit breaker. So I'm actually going to use a separate function that I defined, which creates a custom resilience pipeline that only has the circuit breaker in effect. So this is the policy that we're going to be using today. Let me start running this application, and we can see how the circuit breaker helps to avoid overwhelming our flaky payment service with failed requests. As this starts up, we'll be able to see the Aspire dashboard load. The Aspire dashboard is a great place to look at telemetry while you're in your development cycle and looking at all of the services. You can see we have our flaky payment service running, our order service, and also our web front end. So if I click into the web front end, it's a very simple example where I can just submit some information and submit an order. Let's say we're going to order a raincoat. You can imagine on a nice UI, the user would be able to specify, all of these details would be preloaded. Now, when I hit submit, I'm going to be doing 2 things. I'm going to first be storing this order in Cosmos DB, and then I'm going to be making a call to my flaky payment service. You can see we got an error here. That payment wasn't able to go through, but we didn't trip the circuit yet. As we keep going and submitting more and more orders, you can see we got another failure, and on our 3rd failure, we got this message that the circuit breaker is open. This is because we configured our minimum threshold to 3, and we saw a sufficient number of failures. With the circuit breaker pattern, it's very effective in limiting overwhelming those downstream services. All right, so we have the circuit breaker in place, and we know that we're using microservices. So I wonder if we can use the Saga pattern to help us coordinate consistency across all of our microservices. With the Saga pattern, it allows you to help maintain your data consistency in a distributed system without using distributed locks or 2-phase commits. There's multiple different ways to implement the Saga pattern. You can use an event queue to coordinate events that are happening in all of your microservices, or you can use a coordinator to orchestrate the flow of your application. In our example, we're going to use the event queue. So we know we have our Orders API, which makes calls to our payment service. And we also have our Products API. Now, the Products API is responsible for updating inventory in our products database in Cosmos DB. We have an event queue, which is also hosted in Cosmos DB, and we're able to have all the events that happen from all of our microservices input onto this queue. So we know that our Orders API is a little bit flaky, and when a payment fails, it can emit a message onto our event queue called payment failed. The Products API has a change feed listener, which is listening for all of the events on this queue. When the Products API receives the payment failed event, it can issue a compensating transaction to release the inventory. In this way, the Saga pattern will help us maintain consistency without extreme tight coupling of our microservices. Now, we mentioned microservices a lot, and this is one of the ways you can implement the bulkhead pattern. This is component level isolation. It gets its name from bulkheads in a ship. If a water leak comes in, only one of those bulkheads is actually affected, and the ship is still able to remain afloat. In a similar way, we can use this pattern for our architecture and software to help us maintain resiliency even if something goes wrong. We have our 3 microservices here, and users are able to issue requests and interact with them. We know our orders API fails, so when it goes down, the other components remain unaffected. A similar pattern is the cell architecture. While Bulkhead helps us do component-level isolation, with cell architecture, this is system-level isolation. This is used often for multi-tenancy. With the cell architecture, you have multiple self-contained, independent, and deployable units that are copies of the entire architecture in your system. So we have our architecture diagram here, again, a simplified picture of it. And we have a couple retailers that have a lot of traffic. And I wonder if I can use the cell pattern to isolate them in their own tenant. In this way, I can have a copy of my architecture for tenant 1 and a completely separate copy for tenant 2. This means if one is overloaded or becomes unresponsive, I can still be responsive with my second tenant. With cell pattern, this is redundancy, and it allows your application to be able to better respond to the constraints that are happening in your architecture. The cell architecture is widely used throughout Azure. The ARM team is using cell architecture, and it helped them optimize a large monolithic global deployment they had. They had a single Cosmos DB account with a ton of regions, but it started to lead to a lot of inefficiencies, and they were receiving customer-reported incidents that things were going wrong with this monolithic architecture. Changing to the cell architecture helped them be much more responsive and adaptive. In this example, they have cells that are represented by geography. So you have a geography for the Americas, one for APAC. Within each geography or cell, they still have multiple Cosmos DB accounts, and each of those accounts are still replicated across region. But each cell is independent and isolated, which allows them to be more resilient overall. Okay, so we talked about a lot of phases in the application lifecycle. We went through planning for failures, tips for developing, all the architecture patterns that we can take advantage of. We touched briefly on deployment. There are many phases of this application lifecycle, and we could probably do an entire talk on all of them. However, we're going to skip ahead to maintain. Maintenance is very important to make sure that your application remains available and responsive over time. And for maintenance, it's really difficult to maintain something if you're not able to observe it. Observability is extremely important in reliable applications. There are 3 pillars to observability: metrics, logs, and traces. And all 3 of these can work together to give you a really good understanding of what's happening inside of your application. Observability can be implemented in different ways at different parts of your application. We showed a .NET Aspire app just a second ago, and with Aspire, it uses a lot of defaults, best practices for telemetry. We saw in our service defaults that it adds OpenTelemetry, which is a vendor-agnostic, open-source set of SDKs and tools that help you manage observability in your application. Now, there's also many different observability features that can be provided at the service level. In Azure Cosmos DB, we have diagnostic logs that will help you understand what's going on to the database requests in your application. At Build this week, we're excited to announce aggregated diagnostic logs for Azure Cosmos DB. These aggregated logs offer 5- and 15-minute tables that aggregate all of your data plane request diagnostics. Because this data is aggregated, you're able to see a 90% reduction in diagnostic logs costs without sacrificing on the data that you need to actually debug your application and get use out of this real data. All right, let's take a look at a demo to see how we can use these diagnostics logs to debug an issue in our application. Now, unfortunately, I've been hearing from some of my users that the product search has been a little bit slow lately. So let's take a look at our diagnostic logs and see if we can debug what might be the source of this extra latency. I'm going to use a query on our data plane request 5min table. I'm going to look for the maximum duration in milliseconds, so the highest latency requests. And let's just see what operations we have, what resource types we're making calls against, all the collections that we're calling, and also the region. And we can render all of this as a time chart. When I run the query, we see a nice graph generated for us. And I can see there's a spike here. We did see a latency spike, and it looks like it was queries on our products container. That makes sense since my users were complaining that our product search was slow. We can run a query based on our query runtime statistics table, and let's just see what are the actual queries that we're running against this container. I'm going to search for the specific collection, our products collection, and I'm going to parse the query text. Now, I've already turned on full text query for this Cosmos DB account, which means for all the queries that are run, I can actually see the text of that query, which helps me analyze how can I modify my database to serve that query better. So let's run this, and we can see how many requests of each shape were actually being run. It looks like I have a lot of queries by brand and also a couple queries by category. Now, my products container is partitioned by category. And I have 10 physical partitions in my products container. This means that queries by category are very efficient because the SDK knows exactly which partition to go search for and serve the data back. However, all those queries by brand actually end up being cross-partition queries. The SDK doesn't know which partition has data by brand, and maybe all the partitions do. So we need to go check every single one. This can add a lot of latency to our application by having to check multiple physical partitions. So let's take a look at our Cosmos DB account and see if we can do something to fix this. This is my products container, and as you can see, we are partitioned by category, and I have all the information about my products here. Now, I can use a new feature in Cosmos DB called Global Secondary Index. I've already created a Global Secondary Index container that's called Products by Brand. When I look at the items of this container, you can see my partition key is now on brand. So all of these queries by brand can be targeted towards the Global Secondary Index container, and that makes them a single partition lookup. They should be a lot more efficient and also less expensive to run in Cosmos DB. With global secondary indexes, these are read-only containers. So I only need to make my updates one time to the main product container, and Cosmos DB will automatically update all of the data for me in the GSI. This means that my GSI can be serving all of my queries, and I don't need to worry about maintaining it manually. Let's go back into our sample application and see if we can run some queries against both of these containers and look at how the request is different based on which container we're targeting. I have a simple console application here, and I'm going to run two queries. First, I'm going to select 1,000 products where the brand equals Zavana, and I'm going to execute these queries on both my source container and my GSI container. The next query that I'm going to run is also searching by brand, but this time we're going to run a contains. This is essentially a range filter where I'm looking for a subset of documents within this brand, and we're going to look specifically for some gloves. So let's go ahead and set this as our startup project and run this sample application. Now, as I'm running this, you can see all of the round trips that are being taken to execute my query. When I executed the query against my products container, because remember, products is partitioned by category. So to get all of the products, I need to actually go to all of the physical partitions and see which data lives on each one. And this is represented really clearly here by all of these round trips that I had to take. While each round trip maybe is executing quickly, my total execution time is actually quite high. It's over 6 seconds. And I had a request charge of 46 RUs. Now, when I executed the exact same query against my global secondary index, I noticed that the execution time is way lower. This is less than a second. So all of this latency is just translating to a better user experience. With the global secondary index, I'm able to change the physical layout of my data to better serve queries for my users. If we look at the execution times and the RU charges, we are seeing big savings here. Now, 46 to 31 RUs maybe is about a 40% reduction in RUs. For a single request, maybe that's not significant. But remember, this is a global e-commerce website that I'm running. And at scale, this actually translates to a lot of savings. Now, if I press enter and I start running my second query, remember this one has both the brand, but I'm also filtering even further to get even fewer items returned. We had 70 items that matched this query. Now, this is a more realistic query that users would enter. Usually they have some idea of what they're searching for. And you can see here, we still had all of these round trips against our source container. We still needed to check every physical partition, but each physical partition had a very small number of items that we were actually finding. The execution time was low for each trip, but the overall execution time was over 3 seconds. And we found 70 items back. This query took us 85 RUs on our source container. Let's see what happened on our GSI container. So for the GSI, still we had one round trip. We were able to go to one physical partition to get all of our data because our GSI is partitioned by brand. This time, we can see a 90% savings in RUs because we have much less data being returned. So when you think about your RU charge, it comes from multiple places. In our previous query, where we were getting 1,000 items back, it takes a certain amount of work to retrieve 1,000 items. Regardless if you run that on the GSI or on your products container, you still need to do the work to actually load the items. Now, in an e-commerce website, nobody is searching through 1,000 items at one time. It's not a realistic query, right? So if we look at our second query, which has more filters and is returning about 70 items, this is a reasonable amount of products that someone might be searching for on their site. And we see way bigger savings due to the GSI because the amount of RUs that is coming from checking all of those physical partitions is higher than the amount of RUs that we save, just by going to only one. So this shows you the true power of GSI and how used in different ways for your container, you can see even better savings in both cost and latency. Now, we did one more thing on our GSI container to continue optimizing it, which is we added a composite index. Because our GSI container is implemented as a container, we're able to add any container policies and properties that we can on any normal container. If I take a look at my scale and settings and I look at my indexing policy, I added a composite index on brand and name. So with global secondary indexes, it's important to still remember all of the best practices for Cosmos DB queries and indexing that you know on your normal container and apply those to the GSI for even more tailored and better performance. Because of this composite index, we had an equality filter on brand, and we had that range query for our contains on the name property. The composite index is also driving these RU and latency savings for our user. All right, so we just saw an example of global secondary index, which is announced this week at Build in Preview. We saw how it uses automatic data syncing so that you only need to do your updates into the source container, and they're automatically replicated into your GSI container. We saw how it can increase query efficiency and combine with other query efficiency features like composite indexes in Cosmos DB, and it also improves the developer productivity. As a developer, I don't need to worry about manually syncing these containers. I don't need to manage rights and conflict resolution and errors. It's all handled automatically for me. All right, so now we have our e-commerce website. We were able to plan for failures that may happen in all of the various failure modes, our networking, our application layer, and our database. We were able to implement 5 architecture patterns that help our application remain highly resilient. And we were able to further optimize it by implementing monitoring along the way so that we can react to changes in user patterns and maintain highly resilient and performant over time. Now, this was a lot of content, and I want to leave you with several resources. I have a link to the well-architected framework, several links for Azure reliability best practices, a link to Cosmos DB reliability, AKS reliability, and lastly, a GitHub repo with both the circuit breaker and global secondary index examples. All right, thank you so much. Do we have any questions? I think we have about 10 minutes left.
How do the global secondary indexes impact writes?
Yeah, that's a great question. So with Global Secondary Index, this is an asynchronous index. So it's not impacting the writes to your source container. Your source container writes will remain efficient and performant. It will asynchronously replicate into the GSI container. So your GSI container will have those writes. So you'll have the RU charges and everything for the writes, but it doesn't impact the workload on your actual source container. And this is great because it gives you isolation for various parts of your workload. If you want to isolate certain functionality only to the GSI, it doesn't impact your source container at all. So your existing flows can remain performant and at the throughput levels that you currently have.
If you have multiples, do they run in parallel?
Yeah, so the question was, if you have multiple GSIs, do they run in parallel? Yes, you can define multiple GSIs for a single source container, and they'll all be independently updated. Yeah, and that's automatically handled for you for Cosmos DB. Yes?
How granular can be the consistency modes in Cosmos?
Yeah, that's a great question. So the question was, how granular are the consistency modes in Cosmos DB? We mentioned those 5 different modes. So when you provision a Cosmos DB account, you choose a consistency mode for the account. So that's the top level, the account. However, at the client level, you can override the consistency at a couple of different places. You can override per Cosmos client. So I showed you in our Aspire app where we had all those configurations, options for our client. One of the configuration options is consistency. So at the client level, you can say, hey, for this entire client, I want session consistency. The third override is at the request level. So for an individual request, you can update the consistency. Now, it is important to mention you can only downgrade consistency. You cannot upgrade. So if your account is session consistency, you can't ask for a strongly consistent write, but you can always go down.
Hi. In the case of the multi-region deployment with active and active, and I'd like to have the request being attended to a closer region, even with this new feature about the failover, I will still need to use the multi-master, right, to avoid for one request coming from a region being written in the other region and all the latency between this transaction.
So when you have an active-active setup in your application, you configure which region is the preferred region for that app. And even in a single writer or multi-writer, you still pick a preferred region. So let's say you have a single writer account and your application is deployed globally. So your write region is West US, but you have an instance of your application in East US. For the East US instance, in your client settings, you can specify what region you want to talk to. So because that app is in East US, you can set the region to East US. Now, in a single writer account, you only have your writes going to one region, so your writes will still automatically be sent to West US, which is the write region for your account.
Following on that thought, for highly available systems like payments, to send everything to one region in a single writer mode is kind of defeating the purpose of active-active. Like, if that goes down, the whole thing goes down, right?
So with per partition automatic failover, that's the beauty of it. It is still active-active because if a single partition goes down, you can actually reroute. The SDK automatically reroutes traffic to the live partition in another region. So you have a single writer, but at the partition level, they can be failed over. Now, this is the difference between a blackout where all of your partitions are experiencing issues and you have total availability loss. In that case, Cosmos DB actually behaves really well and can fail over. But imagine you have 100 physical partitions and only one of them is failing. You don't really want to fail over the entire account, but you still have these failures happening. So with per partition automatic failover, even in a single writer account, that individual partition can be failed over and issue its rights in a healthy region until the primary region comes back online. The SDK automatically reroutes back to the primary region. So with PPAF, per partition automatic failover, you get the benefits of active-active while still having a single writer architecture.
So what would be the latency for the failover to actually happen?
Oh, the latency for PPAF, the failover is roughly 2 minutes or less.
Okay. Thank you.
Yeah. Yes.
Global secondary index going to impact the size of the Cosmos DB? If yes, then how much?
Yeah, so the question was if global secondary index impacts the size of your Cosmos DB account. So when you add a global secondary index, you're effectively creating a copy of data in another container. However, with global secondary index, you can control how much data is written. So we offer, you define a query which indicates what properties of the main source document you want propagated. Let's imagine you want only a subset of properties, based on the query pattern for your GSI. You don't need, every property. You can project specific ones into the GSI. So it's at max a duplicate of your source, and at minimum, however many properties you select, it can be smaller than that.
In the container with the replication, we have increasing in the RUs for the common operations because this replication in another containers or not?
Yeah, that's a great question. So with GSI, your source container remains largely unaffected. There is an added workload of change feed. So change feed in Cosmos DB exposes any create, update, or actually global secondary index uses our all versions and deletes change feed, which exposes creates, updates, and deletes. So you'll have that extra change feed workload running on your source container. Depending on your current utilization of throughput on your source, you may have to increase a little bit, but in general, it doesn't impact operations to your source. And with your GSI container, it's a completely separate container. So you can have its own container throughput settings depending on the requirements for the GSI. Typically, it's a scoped part of your workload. It may not need to be the exact same throughput as your source.
What's the latency between the GSI and the main write?
Yeah, that's a great question. So there is going to be some latency. It's eventually consistent system. So we don't have any SLAs that we guarantee. And you're able to monitor this in our Azure metrics. We expose, it's called Materialized View Catch-up Gap in Minutes. We renamed the feature. The former iteration of this feature was Materialized View, so the metric still has a little bit of the old name. It will be updated. So you're able to monitor the lag. And if the lag is too high, you can look at, maybe writes are being throttled on your GSI, you need to scale up. So it depends. All right, any other questions? Okay, thank you guys. Please take the session survey, and I hope you enjoyed the session. Thank you.